Yeah, so I was asked to review X-ray sources, and last night I was trying to assemble my talk. I felt like I was trying to squeeze last 30 years of X-ray astronomy into 20 minutes. I have plenty of slides, so feel free to kick me out when it's time to go through the trip. This nice image, it's a Chandra image of Andromeda Galaxy, of the inner part of the bulge, summarizes the main component of X-ray emission, which I'll be talking about, which contribute to the X-ray output of the galaxy, star-forming or normal galaxy. These are X-ray binaries, accreting neutron stars and black holes. Most of these points are X-ray binaries in MVD1. These are accreting white dwarfs, a specific kind with this table where parameters are right and they have stable nuclear burning, hydrogen fusion on their surface, and they are extremely bright and extremely soft sources. Then there is also some of them, the redder ones are those. And then you see the glow, which is made of emission of a hot ISM, truly diffuse component, and also some combination of various unresolved sources, tens and hundreds of thousands of them, of low luminosity sources. As I understand, there is a couple of people sitting in this room who would want to hear a clear answer. Like best answer would be a clean spectrum from Kiwi range to a Rydberg range of entire spectrum of entire X-ray emission of the galaxy. Unfortunately, I cannot deliver that. We have various components and pieces, which I will show. I'll be jumping back and forth between high mass X-ray binaries, low mass X-ray binaries, star-forming galaxies, elliptical galaxies, and try to give the best approximation to the answer to this question. There is one significant limitation which some of you may not realize, or maybe you do, that because of ISM absorption in our galaxy, and most importantly intrinsic in the target galaxies, we cannot do observations, X-ray observations below roughly half a keV. Everything, well, sometimes for elliptical galaxies we can get down to maybe a few hundred electron volts. For spiral galaxies, for star-forming galaxies, it's worse because absorbing column densities are larger, and it also depends on the hardness of the source spectrum. But basically, as a rule of thumb, half a keV, this is how far we can get. This is why all the observed calibrations, scaling relations, they would start at half a keV. X-ray binaries, well, probably I don't need to spend too much time here. These are accreting neutron stars and black holes, and the energy, gravitational energy is released in the accretion disk. And in sub-Eddington regime, we understand them quite well. It's a standard Shakura-Sunyaev disk with some deviations, disruptions, etc. But we can model them quite well, and the modeling agrees with observations, and we can predict the emission of such a disk in a very broad range, including to the range where we don't really observe it. In super Eddington regime, picture becomes much more complex, and actually we are dealing with sources which we don't quite understand, as I will say later. Speaking of the X-ray output of the galaxy, there are two types. We should make a distinction between two types of binaries, depending on the mass of the donor star. If the donor star is massive, they call high mass X-ray binaries, then the time scale of everything is very short. It's within 100 million years. If the donor star is a low mass star, like solar mass star or less, then the time scale becomes giga-years. And this is illustrated here by binary evolution calculations, showing that there was a star formation at the time 0, and this is how m dot, the mass transfer rate, that means X-ray luminosity of the system, develops with time. This is, we attempted to simulate Cygnus X1, the prototypal high mass X-ray binary, and you see that it happens at about 10 million years after the star burst, after the star formation rather, and lasts for maybe a fraction of a million years. And like a Scorpio X1, a prototypical low mass X-ray binary, it takes it almost 8 or 7 or 8 giga-years to start to mass transfer to star, and X-rays started to being produced. And then it would be the right thing to say that high mass X-ray binary should be scaled with star formation rate, and low mass X-ray binary should be scaled with stellar mass. And then, of course, in the population you have all kind of parameter combinations which give the switch on times in the whole range of values for those, for this and those. And then you can imagine that the time dependence of the output of the galaxy, X-ray output of the galaxy due to X-ray binaries, does something like this. Star formation event at the time 0, some delay before first black holes and neutron stars are formed, or black holes, the shortest delay, then high mass X-ray binaries come into play, then something happens, we are not sure, probably there is a gap, And then low mass X-ray binaries at the giga-year time scales, low mass X-ray binaries come to play, and then they also do something. We're not sure what exactly they do. Now, what observations say? This is our attempt with Pavel Shtakovsky to measure this part using Magellanic Cloud data, and this describes how the population of high mass X-ray binaries in Magellanic Clouds changes with time after the star formation. After the time of the star formation, these are measurements. Well, this is core collapse supernova rate. It's not, doesn't matter here. Here is one caveat. These are pretty faint sources. Luminous sources will be doing everything similar, but earlier or much earlier. Well, they would probably peak at some below 10 million years. For low mass X-ray binaries, we don't see really very significant dependence. This is a collection of elliptical galaxies. Of different, well, passive galaxies, let's say, of different stellar age, and this is some normalization of the population, specific population, number of, or luminosity of low mass X-ray binaries per unit stellar mass. And each point is one galaxy, these are NGC numbers, and you see, well, there may be some trend, maybe not. It's also polluted by the correlation of population of globular clusters with age, but it doesn't matter, it's almost flat, it's a linear scale here. Now, what theory says, this is a calculation by a large group of people using Belchinsky code, a paper by Fragas et al. This is what they predict. This is an output per 10 to the 10 solar masses of X-ray output of the galaxy. These are high mass X-ray binaries. This is the gap which I showed. They do have it in their calculations. And then these are low mass X-ray binaries. But the problem here is that they predict, and the low mass X-ray binaries peak at about 1 giga-year. And the problem here is that it falls down by 2 orders of magnitude from 1 giga-year to where we are now for most elliptical galaxies. And these are observations. These are observations from Borisson et al. They are similar to Jean Blies' observations here. It's basically they're fully consistent. But what we see that it's flat. It's independent analysis. And this is what the theory predicts. Now, question, of course, there are 2 possibilities. Theory is wrong or observations are wrong. The measurement itself of X-ray luminosity cannot be wrong. It's pretty much straightforward. But what can go wrong? Galaxy dating. Like the youngest galaxies may be assigned dates which are not that accurate. That's a possibility. Initially, I was very skeptical about this modeling, but then we ourselves, doing simulations, population synthesis calculations for white dwarfs, we obtained something similar for white dwarfs. So now I'm less skeptical, as you can imagine.
But these are single bursts of population.
This is single. Well, this is a single burst. This is star formation, star burst at the time 0, and these are ages determined using SSP.
But by what sort of star formation time scales do you have to convolve them to get this roughly flat?
Well, star formation time scale is well, yes, in principle.
You have them star forming for 4 or 5 gigayears.
Well,
right. And a light-weighted age of a couple gigayears means that there are some young stars in it. But
there are also some old
stars.
Well, we did some simulations. I don't have time to speak about this. We did some simulations. At least for white dwarfs, it cannot explain that discrepancy. We didn't check it for this one.
It's got to flatten it.
We can discuss it offline. I mean, it just takes too long time now. Of course, now, well, we're all interested in numbers, in scaling relations for X-ray binaries. These are here obtained using Chandra. It's like it's a rather big sample of a few hundred galaxies, some 10,000 sources, etc. This is scaling relation for high mass X-ray binaries, luminosity versus the collective luminosity. With Chandra, we can resolve all the sources. Collective luminosity, some of their luminosities as a function of star formation rate for various galaxies. A very nice linear correlation here, and this is for low mass X-ray binaries in elliptical galaxies, same quantity, luminosity versus stellar mass. And you see that there is a nice correlation, well, with some dispersion, which is real, but it's not very large. And for a general galaxy, which has star formation and stellar mass, you would expect something like this. So the total luminosity is a sum of the component related to high mass X-ray binaries to star formation, plus it's a linear combination, plus the low mass X-ray binaries component. There are some subtleties that this factor is fine, but this factor may depend on the age of the elliptical galaxy or the stellar population. Like there may be differences, as discussed already, between 1 giga-year-old population and 10 giga-year-old population. But this is, again, beyond this talk. Speaking of particular numbers, the numbers are such that for star formation rate of 1 solar mass per year, we have about half a dozen of bright high-mass X-ray binaries. Bright meaning brighter than 10 to 37 ergs per second, with total luminosity of everything, not only bright ones, about 2.5 times 10 to 39 ergs per second. And this happens on the time scale of less than 100 megayears. In all galaxies, in all populations, for every 10 to the 10 solar masses of all stellar mass, there is about a dozen of bright low-mass X-ray binaries with collective luminosities which is about 10 to 39 ergs per second. These are the scaling relations. This happens on this time scale. We can ask what is the total luminosity star-forming galaxy or any galaxy. It's not just binaries, there is also gas, etc., as I explained at the beginning. And this is the scaling relation for total luminosity. In this band, remember again, I'm starting from half a keV here. And it's actually, it's also linear. There is a lot of galaxies, including galaxies from Chandra deep fields, north and south. Star formation rate again all the way up to 1,000 solar masses per year luminosity. About 2/3 of this luminosity comes from, in this band, comes from X-ray binaries, from high-mass X-ray binaries. There is RMS. It is calibrated. The CDF galaxies, they go all the way to the redshift of about 1.5. So it's calibrated more or less up to this redshift on limited sample of few dozen sources, galaxies, but it is calibrated. And there is also evidence, well, not an evidence, but there is argumentation based on the brightness of the CXB that the scaling relation cannot be much different up to the redshift of 2 or 3. It can only be significantly different beyond this redshift. It's interesting to see at the luminosity function.
Is there any reason to believe it would be different with redshift at all? I don't think so.
Metallicity is different.
It makes a difference to high-mass X-ray.
Yes, it makes a lot of difference.
Okay.
But at least up to this redshift, we don't see effect of metallicity. Although you probably don't expect significantly different metallicities with redshift. To have an effect, you have to go down to 10 to minus 2 solar.
Oh.
To have an effect on
Yeah,
binary, or 1/10 of solar at least. Luminosity functions. Well, there is a lot of X-ray binary science in this plot, which I am not discussing here. They are different from low mass and high mass X-ray binaries, but what is important for high mass X-ray binaries, it's a power law with slope of 1.6. That means that the total luminosity of the galaxy is defined by the handful brightest sources. And as you see, these are the sources which are least know about it. For low mass X-ray binaries, it's mostly determined by sources around 10 to 38 erg per second in elliptical galaxies. We understand these sources pretty well. We can do extrapolations to the low frequencies, etc. So they are much easier. Why I said it's difficult for high mass X-ray binaries, because this is the Eddington limit for 10 solar masses object. And we see like bright sources which exceed the Eddington limit, this Eddington limit by a factor of up to 10. And such sources, well, there is no normal standard theory to describe accretion disks in these sources. There are ideas, there are different proposals, but there are no checked, verified theory. So this is why predicting, doing any extrapolations of luminosity of high mass star-forming galaxies is somewhat difficult. You need to consider various possibilities.
So that's equivalent isotropic luminosity?
Yes, it is. It is, we know that they are isotropic from ionization nebula, from planetary nebula ionization energy balance. Spectra, I'm not going to show the total spectrum of a star-forming galaxy, but I just show what are the components. So if you look, this is a luminosity function. This is luminosity range from 10 to 35 to 10 to 40. Different luminosity parts are occupied by different types of sources, pulsars, black holes, ultraluminous X-ray sources, and they have vast variety of spectra. And the main contributor, well, black holes, they also have spectral changes, changes of spectral states, where they have vastly different spectra, like here, for example, this is Cygnus X1, it can change it dramatically. But the most important contributor to the total emission are, of course, ultraluminous X-ray sources. We were just starting to understand observationally with the launch of new star. Before that, we only had from Chandra just the bit of the spectrum here. Now, I'm finished with X-ray binaries for the time being. Thank you. Unresolved emission. So these are the spectra of unresolved emission in different types of galaxies. These are stacked in the work we did with Akis a few years ago. Star-forming galaxies in blue normal elliptical galaxies in red, and this is massive elliptical galaxies. So there is a soft component which comes from hot ISM with a temperature of a few hundred of electron volts, and there is this tail which comes from faint sources, faint X-ray binaries, CVs, stars, etc. Maybe also some contribution from ISM. It exists, it's equally present in elliptical galaxies and in star-forming galaxies. Now, for star-forming galaxies, the hot ISM, this component, correlates pretty well with the star formation rate. This is from paper with Stefan and Mineo, and apparent luminosity is easy. It follows this relation, and it's some fraction of high mass X-ray binaries luminosity, but these are very soft spectra with a temperature of quarter keV, and the intrinsic absorption in these galaxies exceeds 10 to 21 per square centimeter. If you try to do bolometric correction, absorption correction, you come up with the correction coefficients of order of 10. That tells you that it's not very reliable. I would say it's very unreliable. Nevertheless, if you want a number, this is the number produced to the best of our knowledge, and it's at a level of 10 to 40. It's almost 10 times brighter than high mass X-ray binaries, a gas. While faint objects, they are not so interested. Now I'm talking about those guys contributing here. They are not so much interested. They correlate with star formation rate, sort of, with some dispersion in star-forming galaxies, with stellar mass and elliptical galaxies, but they don't contribute much. They contribute just a few percent to the total luminosity. Again, in this band. What happens below this, we don't know. We think that there is nothing dramatic happens there, but we don't know exactly. And this is again faint sources, the luminosity function of faint sources and bright sources in elliptical galaxies. This is a whole range of luminosities from 10 to 27 to 10 to 40, low mass X-ray binaries, CVs, ABs, and like you can see the numbers, it goes from 100 per galaxy per Milky Way, in a Milky Way, to 10 to the 8 sources. Very faint. There are very many very faint sources, but as shown here, they don't contribute more than 3% to the total luminosity of the galaxy. Finally, accreting nuclear burning white dwarfs. As I said, if the range of parameters is mass accretion rate and mass are in the right range, then hydrogen will burn on the surface of white dwarf, and that would produce up to 30 times more energy than the energy of accretion. Okay, it's different for neutron stars. For white dwarfs, it's this. And then, well, we did the population synthesis calculations. Best way we could do, Halian Chen, my PhD student in Garching, spent a lot of numbers of computing hours in Yunnan Observatory, the supercomputer of Yunnan Observatory, and he produced this using mesocode, where we do evolutionary calculations for every binary, basically. And this is a prediction. This is what the spectra of these sources are. They are pretty soft, as I said. This is 100 angstrom. This is 10 angstrom, 1 keV. They are pretty soft, and this is a prediction of their luminosity in X-ray band from 0.3 to 0.7 per unit stellar mass, and you see it peaks at 10 to the 9 years, at 1 gigayear, similar to lower mass X-ray binaries. It does something like this. Also, while knowing the spectrum, one can compute the helium, hydrogen, helium ionizing luminosity, which is shown here. Interesting to compare it with stellar population. It's about 1.5 order of magnitude at the peak, exceed the contribution of stellar population, including the post-AGB stars. So this may be interesting, but there is a problem. Because if we compare the prediction of the theory of this calculation with observations, X-ray observations with Akash-Bogdan of these galaxies, I'm almost done, or helium-2 line, I'm not going into the details, it's coming from the ISM, which was discussed at one of the previous talks, due to ionization of this ISM by hot sources. And while there is a discrepancy at early ages, if you remember the plot I showed in the beginning for lower mass X-ray binaries, it's very similar. So again, either theory is wrong or galaxy dating is wrong. We think here, we check the galaxy dating, and there is not much, well, actually in connection to this plot, there is not much room for it to, even if it's wrong, it doesn't change the picture, but still there is more work to be done. And the theory, it's both low mass X-ray binaries Fragus result, and this one based on the same population synthesis principles, the same ideas, even though, well, we did it better, but it's the same underlying assumptions. So that should be taken, predictions for white dwarfs should be taken with a grain of salt. And this is now my attempt to plot the overall spectrum of the galaxy It's a retired passive galaxy, 1 giga-year old. These are stars computed using Gruisard and Charlotte code. These are post-AGB stars, which go all the way beyond the helium-2 ionization threshold. These are X-ray binaries. This is gas. Well, as you heard already, there is a lot of dispersion in gas luminosity, so it's closer to the upper envelope of the gas luminosity for given mass. It's all normalized to solar mass, and these are white dwarfs. Okay, which may be a very interesting contributor beyond the helium-2 few Rydberg
What's your star
frequencies.
formation rate for the stars?
There's no star formation rate. It's an old galaxy. I cannot.
This is a passive
I
galaxy.
don't have. It's a passive galaxy. I don't have such a plot for star-forming galaxy. It's still in. We're still working on this. And this is how we change for all the galaxies. White dwarfs go down and stars go down. Well, there is a caveat here that actually, well, there is dependence. As I said, there may be dependence of gas on H and X-ray binaries on H, which is not included in this plot. I only vary these things. This is based on population census calculations of Halian Chen, and this is based on Gruisard Charlotte. And these are calibration obtained for local galaxies. Thank you.
Question from our
On the low mass X-ray binaries and discrepancy with the models. If I remember correctly, those models don't include the dynamically formed low mass X-ray binaries.
No.
And we see that in global class especially, there are more of these sources. Do you think that if you include the dynamically formed X-ray binaries, you can calculate going through those?
No, there is evidence that it doesn't. Well, I don't think it does. And secondly, there is an evidence that it doesn't. There is a paper where by Brett Lemmer, where they tried to remove contribution of globular clusters from their data, so that they compare apples with apples. And while it actually changed it a little bit to the better, it's still open question.
Can I respond briefly to this? I mean, even the central densities of early type galaxies, even L-star early type galaxies, are not nearly that of globular clusters, even the least dense globular clusters. So the question is whether or not the dynamical effects in
Globular clusters.
in the ellipticals are the same as the
I
globulars.
mentioned globular cluster because...
Oh, you mean just the globulars? Okay.
Yeah,
Because
sorry.
from observations, we know
Yeah.
that up to half of the X-ray sources, X-ray binaries, are in globular clusters in
Yeah.
massive having large populations with
Crystal?
clusters.
question regarding the smooth X-ray emission. So, what fraction of this is due to X-ray synchrotron emission of supernova remnants?
Well, I don't have a number. I don't know the number. If it can be separated spectrally, this can be done. But this is like if you saw that the spectrum has a solid pump and then some tail, which we
Exactly.
mostly ascribe to complex sources, but there may be contribution from them.
Further questions from Mara? If not, let's think of. Oh, sorry. No, Brett had a question.
Fine. I was just going to ask about this new accreting white dwarf ionism spectra. If we look at post-starburst galaxies, for example, in this slide, which should be around the age where you expect this accreting white dwarf to think, we don't see either strong helium-2 or strong oxygen-3 emission lines from this. So, yeah, I mean, like that's a huge...
This is consistent with what we're not selecting post-starburst galaxies while we're trying to walk in this direction, but this is consistent with the conclusion based on this stacking of retired galaxies. Like they are the helium-2 to H-beta ratios are compatible with what you expect from post-AGB stars without any populations of such forms.
Exactly.
Okay. Let's thank Marat again.